Hello, this is Paul from the Astronomy for Insomniacs channel. Today we're going to use Pixinsight to combine pictures taken with different telescopes and camera combinations and see whether we can create a single image that contains both wide and narrow field content. The original goal of this workflow was to enable a community result so that a group of astrophotographers with refractors, reflectors and various skill levels could contribute to a single result. Of course, the same idea applies to a single astrophotographer working with multiple telescope configurations. Let's take a look at the images we're going to combine. Dataset 1 is a wide field of M81 and M82 taken in April 2025. The telescope is a Takahashi FSQ 106 refractor with a 530mm focal length. That's paired with a ZWO 1600mm Pro, so a mono camera using RGB filters. As you can see, this combination provides a large field of view, giving a pixel scale of just under 1.5 arc seconds per pixel. Dataset 2 is of M81 and has a much narrower field of view. The telescope is a TPO 12-inch RC, Richter Crichton, with a 1790mm focal length, and again uses the ZWO 1600 mono camera, but with RGB and HA filters. The image scale is 0.438 arc seconds per pixel, which is much bigger than the previous image. Our last dataset, dataset 3, is of M82 and has a narrower field still and was taken in May 2026. The telescope, again, is a TPO 12-inch Richter Crichton, but with a 2022 focal length and a ZWO 2600 MC Duo, which is a one-shot color camera, and it gives us an image scale of 0.303 arc seconds per pixel. All three images have been previously plate solved using Pixinsight's image solver script. You can easily pick up the image scale if you look at the process console when you open the target file. The general workflow is to use a mosaic approach. Each linear image will be registered using mosaic by coordinates, made to match each other by David Alt's DNA linear fit script, and I'll give a link in that in the comments, and finally composed together by the gradient merge mosaics process to give us a single combined master ready for further processing. The first challenge is getting all three images onto the same coordinate system despite their very different scales. For this, we use the mosaics by coordinates script, which doesn't just align pixels, it reprojects each image onto a shared astrometric grid using the plate solution we embedded earlier. This is why plate solving wasn't optional. Mosaics by coordinates must identify matching stars and structures despite the difference in image scale. If you don't choose a resolution, mosaic by coordinates will default to the finest resolution it sees. In our case, M82 at 0.303 arc seconds per pixel. That's nearly 5 times finer than our wide field image. But because we're dealing with 2 dimensions, the output canvas will be roughly 25 times larger in pixel count. My wide field master is 192,000 kilobytes. So we're immediately looking at an output of around about 4.8 gigabytes. And then gradient merge mosaic, which we'll use later, doubles that again by outputting at 64-bit precision. So we could be heading towards 10 gigabytes from 3 modest input files. Choosing the wide field resolution of 1.474 arc seconds per pixel keeps the output sensible. Mosaics by coordinates has completed successfully and has given us 3 images aligned to our pixel scale. You might also notice that these images have a new suffix, MBC, a suffix we'd specified in the parameter text. You can see that the narrow field M81 and 82 images now fit the wide field image. Before we can blend these panels together, we need to ensure their brightness levels are consistent, not just visually similar. Linear Fit analyzes the pixel intensity relationship between images and calculates the scaling needed to bring them into agreement. Without this step, panel boundaries would show as visible seams in the final mosaic. Because the mosaic bi-coordinate script leaves dark unpopulated regions at the panel edges, standard linear fit doesn't work so well. So I'm using DNA Linear Fit, a script by David Alt, which is specifically designed to handle that situation and sample only the valid overlapping pixel data. I've opened the DNA Linear Fit script and have chosen the mosaics by coordinates modified wide field of M81 and 82 as our reference image. Our target images are the MBC versions of M81 and then separately M82. Once the DNA Linear Fit script completes, I will do individual screen stretches, that's just Control A of course, just to visualize them and save all three images in a new folder, ready for input into the Gradient Merge Mosaics process. DNA Linear Fit has completed. Our separate M81 and M82 mosaic by coordinates image have had their brightness rescaled to match the combined wide field image and have been saved. Now we're going to combine these images using Pixinsight's Gradient Merge Mosaic script. We start by loading our image files. Note that you can't add open views here. You need to load from disk. Gradient Merge Mosaic offers two combination methods, overlay and average. Average works pretty much as you'd expect. It combines pixels based on the values across all input files, and the order you load them in doesn't matter. Overlay needs a bit more thought. With overlay, images later in the list will overwrite the earlier ones in the areas where they overlap. So, if the wide field image is the last in the list, the output is essentially just the wide field. The narrow field data never gets a look in. If the wide field is first, then the individual M81 and M82 images replace the wide field content wherever they overlap, which might actually be what you want. Using the higher resolution narrow field data to replace the wide field in those areas. Pixinsight does let you reorder the file list, so you have full control over the priority. I've noticed that average seems to create pinch star artifacts more often than overlay, though it happens with both methods. Stars will have slightly different PSF characteristics on each panel, and those differences tend to produce artifacts along the seams where panels meet. You can adjust the shrink radius and feather radius parameters to reduce these artifacts, but in my experience, it quickly becomes a game of whack-a-mole. Fix one seam and something appears elsewhere. So I have a couple of techniques I prefer instead. The easiest way to find the offending star is to place the Gradient Merge Mosaic output over the mosaic by coordinates wide field image. The pinch star becomes immediately obvious by comparison. Remove it from the wide field source using clone stamp, recombine with Gradient Merge Mosaic, and it's gone. An alternative is to use a star removal tool. Typically the artifact lives in the starless image, and once the stars are out, you can use something like SETI Astro's Blemish Blaster to clean it up, then add the stars back. You might be tempted to just crop the narrow field panels to push the problem star outside the seam. I've tried it, And in my experience, the artifact simply relocates to wherever the new seam falls. One more practical note. The output of Gradient Merge Mosaic will be in 64-bit format, which doubles your file size. Save in 32-bit and you'll save yourself both time and storage with no meaningful loss. Since my goal here is to create a coherent combined image from multiple contributors rather than privilege one over another, I'm going to choose average. Gradient Merge Mosaic has now finished, and our combined image is ready for the standard processing workflow. For me, that's Blur Exterminator, Noise Exterminator, then Multiscale Adaptive Stretch. Here's the final result.